right, organic chemistry. So we skim the surface here on the fact that carbon is all around us, that we are carbon-based individuals, organisms, and there are many organisms that are carbon-based. And so we've talked about carbon a little bit already. So we remember that carbon has an atomic mass of 12.011 and it has an atomic number of 6, which tells us that there are 6 protons, there are 6 electrons, and if we were to subtract the 12 minus 6, we have about 6 neutrons. This is kind of an example of what carbon looks like. And here's kind of our Lewis dot diagram with our electron shells. So here's our our nucleus in the middle. 2 electrons fill the first shell, 4 the outer shell, which means that we're unstable, but we're really looking to have the ability to bond with a few other elements to make this octet rule 8. And so carbon most times is in covalent bonds with other elements. So we looked at this last time we met together, and we were able to see that carbon, okay, has bonding because it has 4 outer electrons, and so it has the ability for 4 bonds. So that might be single bonds, it might be double bonds. It just depends on what it's bonding with. So last time I gave you the example of CH4, which was methane, and so each one of these hydrogens shared an electron with their carbon, and so they were each happy, and their electron shells were basically full, whatever shell it was. The other example here was CO2, and we looked at this last time as well. And here as a double bond. So basically, each of these oxygen is happy in their octet rule with each carbon pair electrons that it pairs up with. Because of that, makes carbon very, very flexible and universal. We can talk about them being in chains, but they can also form rings or spheres with one another. So each one of these little points, so you can see, let's look at this one for example. This says C10-8H, which means that there are 10 carbon and 8 hydrogen. So you can see each point of this sphere, excuse me, is a carbon. So here is, they're numbered 1, 2, 3, 4, 5, 6, 7, 8, and then there'd be a 9 and a 10 right here as well. And then obviously we're going to have hydrogens bonded off of those. So you can see that they can kind of change shapes and be three-dimensional, which is very, very interesting when you think about it. The other thing that is actually kind of interesting, I'm going to have you look at these two right here, is that this is C14H10. This is C14H10. MP says melting point. So here, this is 207 degrees Celsius. Here is 100 degrees Celsius. They have different names, and their configuration is different. This is a linear spheres, and this is not a linear sphere, depending on where the carbons bond with each other. So just be aware that there is lots of variations here when we get into this kind of spheres or rings of carbon. But carbon also can be a chain, like we said last time. This is methane, so here's 1 carbon and then the 4 hydrogen. And as you can see, there's 2 carbon. Now here there are 6 hydrogen, so on and so forth. So these become what we call chains. If you notice, this is methane, ethane, propane, butane, etc. These are all anes. These are all flammable. These are all kind of accelerants that we might see, and they're definitely carbon-based, but they're not things that we would normally find in our body. These are things that are more flammable and accelerants. Now, carbon chains, the carbon kind of chain that we saw is basically a backbone. So if I go back to my last picture here, this is kind of what we consider the carbon backbone, the skeleton. So carbon is bonding to a carbon to another carbon, and then coming off of all of these are hydrogens. And so we call these hydrocarbons. They're very simple structures. They're just carbon and hydrogen bonded together in a single chain, but they can be very complex because we have what we call functional groups that we add onto them. So they could be very simple like these folks, or however we might take off one of these hydrogen and put a different functional group on there, and that changes what it is. And so we'll talk about functional groups in the next few slides. So our functional groups. Hold on, we're going to get there. Hydrocarbons. So again, this is like showing an example of those hydrocarbons, and that carbon and hydrogens are those non-polar covalent bonds. They form these non-covalent bonds, and therefore they are hydrophobic. They do not like water. So here's just an example of about two different liquids separating out. This is basically water. It just has some food coloring in it, so you can see it a little differently. And this is an example of a hydrocarbon, which is basically some type of oil substance, and therefore it's going to sit on the top. And even if we were to swirl this up in the moment, what would happen is it's going to sit up at the top again. And again, it has to do with the fact that they are opposites. The hydrocarbon oil is basically nonpolar, and our water is a polar substance. So the polarity of them, basically, the opposites attract. Remember the song? Back in the day? That's the truth. The saying is opposites attract, and that is true. But the carbon skeletons, again, have functional groups. And functional groups are part of molecules that basically will kind of determine the polarity of it, how it will react with the whole entire molecule, and so it can change. So here are just 6. There are more, but there are 6 biologically important functional groups. The hydroxyl, which you would see as just an OH. The carbonyl is just CO. Carboxyl is COOH. The amino is NH2, which will look much different. The sulfhydride is sulfide and hydrogen, so SH. And the phosphate is OPO3, so oxygen, phosphate, oxygen 3. These are functional groups that might very well be attached to our chain, right? So they might plunk off one of these guys here, one of these hydrogens, and put one of those functional groups there. And that's going to change how it reacts with something else, how it's going to work with something else, its polarity, etc. So one example I'm showing you here is the amino group. This one is very different. So it's NH2. We call these amines. It's a base, so it can pick up those hydrogen ions out of the solution and again help balance it out. So here is just kind of the chain. We call this the R group. The R group is kind of the chain coming off of that hydrocarbon. And then we'd have the nitrogen and 2 hydrogen, excuse me. That's the amine group. So you might see it here. So again, here is a carbon chain, a carbon, hydrogen. Here's an amino group on one end. The other group happens to be a carboxyl acid group, right? So this COOH group. And again, this is another place where we might have a secondary side chain. So we can have more than one functional group on these hydrocarbons. Here's that phosphate, OPO3. Can be oxidized. It's an organic phosphate. It's really important for the glycerol phosphate. We're going to find this guy in our wonderful DNA structures. Okay, so here's that phosphate group right here, and it attaches to our sugar and then our nitrogenous base. So these are the basic units that make up our DNA. Here's just another example of it kind of hanging out over here. You can kind of see it looks a little different, but that is our phosphate group. So that's the end of our organic molecules. We're going to continue on a little bit more talking about carbon, because that's where we're going to go for the rest of the semester.